Good evening to all of you. Welcome all of you to the webinar of Regional Science Center Tirupati. You know very well we are going for a series of webinars on Nobel Prize winners of this year 2020, and this is the second of its kind. And I welcome Dr. Dwari and my own director of Visvesvaraya Industrial and Technological Museum, Mr. K. Madan Gopal, and many other actually friends from Freebirds, and many of our student members. They are all joining. I welcome all of you, and it's a great pleasure to have Dr. Dwari here, sir. After a long time, I'm meeting you once again, sir. This is a great opportunity for us, as well as we are very much looking forward to learn from you. And the same way, I'm inviting our zonal director, K. Madan Gopal also, and I request Sri Madan Gopal to please introduce the speaker of the day. I hope this is the right occasion. Actually, I'm getting Sri Madan Gopal with us. Thank you so much, sir. I think you can take over and invite the speaker, sir.
Thank you, Manikantan. First of all, let me congratulate the Regional Science Center Tirupati to join hands with Freebirds Experience in organizing this webinars on Nobel Prize. I think most of you must have seen in the newspapers that this year the Nobel Prize in Physics has been awarded to three great gentlemen, or I could call them as three great physicists. And all these three great physicists, that is Roger Penrose, Reinhard Genzel, and Andrea Ghez, they have done a lot for us to understand the concept of something which Einstein predicted in the year 1915. Einstein, in the year 1915, through his general theory of relativity, predicted that a sufficiently compact mass can deform space-time to form a region where gravity is so strong that nothing can escape from the region. And this is something which was called as black hole by John Wheeler. So we should all remember that John Wheeler is responsible for coining the name black hole. Today, as many theories are popping up on black holes, I will not go into the deep of those black holes because we have Dr. Devi Prasad Dwari to explain to us all those aspects. But then I will just tell you one thing: we are not able to see the black holes because they are invisible, but then we are able to feel their presence because of their action on the other objects which are surrounding them. So these black holes are of different categories and different types, and this year's Nobel Prize has been given to three great gentlemen for their specific discoveries, which is once again related to the general theory of relativity. Dr. Penrose discovered that black hole formation is a robust prediction of the general theory of relativity, whereas Reinhard Genzel and Andrea Ghez said that discovery of a supermassive compact object is there at the center of all massive galaxies. So these two contributions have earned them the Nobel Prize this year. Coming to the introduction, Dr. Devi Prasad Dwari is one of, in fact, you know, today we are very much privileged to have you, sir, on this occasion, and for finding time for joining us on this webinar. And it is my privilege to introduce you to all the audience today. And I think I can take the privilege of telling everybody that you are also my good friend, if you agree. Okay, Dr. Devi Prasad Dwari finished his post-graduation from Jadavpur University in Calcutta, and then went on to do his PhD from the Inter-University Center for Astronomy and Astrophysics under the Pitamaha of astronomy in this country, that is Dr. Jayant Vishnu Narlikar. Since then, after his PhD, he has occupied many hats, one of that being a visiting fellow at the Tata Institute of Fundamental Research in Bombay. He was assistant professor at the Institute of Advanced Studies in Basic Sciences in Iran. He was also a faculty at the University of Manchester Institute of Science and Technology in the United Kingdom, and he is presently serving as a Director, Research and Academics with the MP Birla Institute of Fundamental Research in Calcutta. He has contributed immensely to the field of astronomy and astrophysics, and as a recognition to his contribution, special awards have been honored on him. To name a few of that, he has been awarded the Best Thesis Award by the Astronomical Society of India in the year 1993-94, Gopal Chandra Bhattacharjee Memorial Award in the year 2008, Ravindra Puraskar from the Government of West Bengal in the year 2019, and the SOA University in Bhubaneswar has conferred DSc honoris on him. He has been a member as well as fellow of several organizations. To name a few, he is a fellow of the Royal Astronomical Society, is a member of the International Astronomical Union, fellow of the Calcutta Mathematical Society, is a member of the Indian Association for General Relativity and Gravitation, and he is also the president of Manindra Narayan Astronomical Trust, as well as the former president of Institute of Science, Education and Culture. He has delivered several lectures all over the country, rather all over the world. In fact, he has visited several countries like United Kingdom, United States of America, France, Belgium, Netherlands, Luxembourg, etc. The list is a very big list of about 45 countries. Sir, please excuse me for not naming all the 45 countries.
It's okay. It's okay.
But then your contribution to the field of astronomy and astrophysics is immense and is recognized world over. And he has more than 20 publications to his credit in various international and national journals. He has written books, notable books written by Dr. Devi Prasad Duwari, or one is the Mahakasha Sahajpath. It's nothing but a cosmic primer, which has been published by the Department of Information and Culture, Government of West Bengal. And the physics textbook, which is read by all the 9th and 10th class students of the West Bengal government. And he is in the process of writing 2 more books. One book is the Cosmic Concepts and Challenges, and the second book is the India's Space Odyssey. Sir, it is our privilege to introduce you, and your contributions are immense to the field of astronomy and astrophysics. In fact, looking at his teaching profession, he has been an honorary faculty member of the Presidency University, course director for the PG Diploma program in MP Birla Planetarium. He has been the resource person for University Grants Commission. He has been a resource person for Inspire program. And then the most important thing which I am coming to is about the science policy formulation. He has been a member in several science policy formulation committees of this great country. He has been a member of the advisory committee of the Technology Vision 2035, which is the pathway for the growth and planning of technology of science in various aspects. And then he has been member of the National Standing Committee of the Inspire program. He is a member of the Planning and Programming Committee of BITM Calcutta, and is an advisor on school textbooks and syllabus for the Government of West Bengal, and is a member of the Department of Science and Technology, Government of West Bengal, for the book committee. Sir, with your vast contribution, vast experience, we are all looking forward to hear from you to inspire us about astronomy and astrophysics. Sir, I am leaving the room to you, so I would now welcome you to this program and request you to kindly enlighten all of us about your ideas on astronomy and astrophysics, and the most importantly, the concept of exploring the black holes in the universe. Sir, that stage is yours.
It's a wonderful feeling, Mr. Madan Gopal and Mr. Manikantan, to get invited by you people who are both my very dear friends to give this lecture or this webinar on the 2020 Nobel Physics Prize. It's really an amazing feat that National Council of Science Museums, all its field units, the RSC Tirupati, as well as Visvesvaraya Technological Museum, they are on a mission to enhance not only the knowledge base of the general people and students, but also to make India great. Because according to me, it is through our scientific temper, through our scientific understanding, that development will come. And NCSM as a whole, and especially RSC Tirupati, and as I mentioned, Visvesvaraya Museum, both are really working very hard. I have seen that. and I've known that for quite a number of years to achieve that. So it's a special thanks from me, and I'm grateful to you and to the NCSM for giving me this opportunity. Without wasting much word, let me go to my presentation, through which I'll be trying to discuss about the today's topic. We all know that this year's Nobel Prize has gone to black holes. No, that will be too much. Has gone to three wonderful personalities, very renowned scientists who have given us insight into an object, a phenomena, which even 20, 25 years back, people thought is a subject of science fiction, imagination. That is the reason I have titled my webinar as Light in Search of Darkness. Not only darkness in terms of the black hole environment, but also darkness in terms of our knowledge, our understanding about this whole concept. So let us begin. Let us start our journey in the deepest depth of the cosmos, where there are objects which defy our physical everyday existence and understanding. But nonetheless, they are very, very important in our understanding in exploring, analyzing, and synthesizing the designs of nature. As you all know, as have been already mentioned, the Black Hole Nobel Prize, or the 2020 Physics Nobel Prize, has been shared by three top scientists. Half of the prize has gone to Sir Roger Penrose for the discovery that black hole formation is a robust prediction of general theory of relativity, and to two more observational astronomers, Andrea Ghez from University of California, Los Angeles, and Reinhard Genzel from Max Planck Institute for Extraterrestrial Physics. And they have received the prize for the actual discovery of a supermassive compact object at the center of our galaxy. So it is not a black hole, they are saying, supermassive compact object at the center of our galaxy. This 2020 Nobel Prize is very significant, at least for me and for not many people, because as a student of astronomy and astrophysics, if you ask me about the subject, before going deep into the subject, I have to mention that this is one of the most advanced subjects in the present era, being pursued by the topmost scientists and the brilliant minds all across the globe. And that the present generation is really interested in the subject, and huge amount of work is going on because of the technological advances is reflected in the next slide. Because it is a wonderful match between theory and observations. I think hardly any Nobel Prize was given in the same year for the theoretical understanding, explanations, and the actual observation of the issue. So Roger Penrose at one side on the theoretical aspect, and Andrea Ghez and Reinhard Genzel on the other side with the observational aspect, as if there is a fantastic match between these two aspects of any branch of science that has been recognized by Nobel Committee. And also it is wonderful for astronomy. The subject of astronomy, astrophysics, cosmology, general theory of relativity, if you take from the beginning of the Nobel Prize, from 1901 to 2000, there are only 3.5 Nobel Prize awarded to these subjects. Why half? Because in 1978, 50% of the Nobel Prize was given to Penzias and Wilson for the discovery of the cosmic microwave background radiation. But if you take the last 20 years, it is such an exciting experiment, right? 2000 to 2020, 6 Nobel Prizes in physics has gone to astronomy and related subjects. In another way, it is very important, this year's Nobel Prize. Why? Out of the 216 Nobel Prize winners in physics, starting from 1901, only 4 women have been awarded this prize. And this year, Professor Andrea Ghez is the first woman in astronomy who has been awarded the Nobel Prize. So it's a tremendous significance for all of us who love the subject of astronomy, that astronomy is becoming the buzzword of the international community as well. The night sky. Thousands and thousands of years back, when our ancestors used to look into the night sky, they used to wonder, what is sky? What are those objects we call stars? And is there any connection between the star and the earth? With these set of questions and queries, the subject of astronomy was born. So astronomy can be considered as one of the oldest subjects that human minds have dwelt upon. At the same time, given the huge number of news items in television channels, newspapers, internet, you get an idea that it is also one of the most happening subjects in the recent times. Astronomy as a subject can tell us what was the situation in this particular region of space that we live millions, billions of years back. At the same time, it can give us a hint what can happen to this region millions and billions of years later. So spanning a vast expanse of space and time, or space-time as it is called, is the subject of astronomy. And scientists are realizing that soon astronomy will be called as the laboratory of present-day science. Why? Because the most extreme critical theories, where the amount of energy involved is enormous, can be tested in the laboratory of the skies. So astronomy has gained importance. And that is the reason for the last 30, 40 years, a tremendous amount of, as if a revolution is happening throughout the world. Every country, developing, underdeveloped, fully developed, they're desperately trying to build newer and newer facilities, collaborating with each other to create gigantic technological monuments, not monuments, I'll say, technological huge machines through which they're trying to look deeper into the space. Just to give you an idea, atop this once volcanic island, Mauna Kea, in the Hawaiian archipelago, there are almost 9 to 10 observatories, and the smallest one cost is around $400 million, right? So the huge amount of effort. For example, if you take the very large telescope at Cerro Paranal in Chile, huge instruments, 8.2 meters, 4 of them, and they are actually connected to gather all the lights coming in all the 4 telescopes and give us a very clear picture of the sky. But as Indian, I'm very happy that the largest telescope, the work has started, and maybe within 2 years or so, it will start getting functioning, and that will be called the TMT, 30-meter telescope. It is one of the mega projects that Indian government, the Department of Science and Technology, along with some leading institutes in India, is collaborating with 5 other countries to create this fantastic instrument, which will look deeper into the space, much deeper that we have probably seen till today. And it is not only the optical light through which universe is looked upon. We know all the wavelength ranges of the electromagnetic radiation, visible and radio waves, can penetrate the atmosphere and reach the surface of the Earth. That is the reason radio astronomy, for the last almost 90 years, 80 years, is doing tremendous amount of giving input to our understanding of the cosmos. Leaving aside the electromagnetic spectrum, in 1916, rather 15, Einstein's general theory of relativity shocked everybody. They were startled by the revolutionary concept that Einstein's theory gave. But when they worked out, they found out that there should be a presence of a ripple in the space-time which can get originated because of very massive objects, compact. If they come to each other, go around each other, or actually collide with each other. And that ripples in the space-time was called gravitational radiation. And lo and behold, just 100 years later in 2016, using again a fascinating instrument, LIGO, Laser Interferometric Gravitational Observatory, the signal was detected. Until today, I was reading, almost around 50, 60 candidates, gravitational wave radiation candidates have been identified. So the future looks exciting. Let us start our journey from our earthly bounds into space and time. Because we know when you look up in the sky, we are not only going deeper into space, we are going back in time as well. Because light has a velocity of 3 lakh kilometers per second. And the distance, for example, the distance to sun to earth is around 8.3 light minutes. The distance to the closest star to our solar system, Proxima Centauri, is 4.2 years. That means when you look up in the sky, I'm doing a time travel. So I will request my young friends not to really think of going to a science center and spending some money and getting a ride on a time machine to do a time travel. In an open night, in a clear night, go out into the open, tilt your head. The deeper you are looking at your own past. We don't realize that instantaneously. It's an amazing thing. Obviously, we should start from our home, the solar system, with a fantastic sun and 8 planets, 5 dwarf planets, thousands and thousands pieces of rock, meteorites, and millions of pieces of frozen, icy, dirty ice balls called comets. Sun. Sun is the central object of our solar system. And it's a ball of gas. My friend, how come a ball of gas is keeping its shape and size intact and not diffusing out into the space? According to the scientists, 460 crore years back, or 4.6 billion years back, a huge cloud of gas and dust was floating in space. This cloud was made up of, in terms of particles, 91% hydrogen, 8% helium, and 2% rest other elements. In terms of mass, 74% hydrogen, 25% helium, and 1% rest other elements. The average temperature of this gas cloud was minus 240 degrees centigrade. At this extreme cold temperature, out of the 4 fundamental forces of nature, only one type of force comes into play, and that is the force of self-gravity. The force of self-gravity will attract the periphery of the gas clouds toward the center. As the gas goes towards the central density rises. As the density builds up, temperature rises. As the temperature rises, the pressure also builds up. And starting from minus 240 degrees centigrade, the temperature rose to a fascinating level of roughly 1.5 crore degrees centigrade, or 15 million degrees centigrade. At 15 million degrees centigrade, what happens? 4 hydrogen nuclei, as if they come together, fuse together, and produce a helium nucleus, as if I said. All 4 doesn't come together. It's a serial process. But this thermonuclear fusion reaction of 4 hydrogen nuclei, 4 protons, initially giving birth to a deuterium. A deuterium with 1 proton gives you 3 helium, and 2 3 heliums gives you a 4 helium, a stable nucleus, and 2 protons. So effectively, 4 protons giving rise to a helium nucleus and a huge amount of energy. This thermonuclear fusion reaction, when it occurs inside the core of the sun, huge amount of energy tries to flow out. As the energy tries to come out, there is a pressure which builds up from inside to outward, radiation pressure. This pressure, where it exactly balances and matches the inward force of gravity, sun being a ball of gas remains hanging there for millions of years without dissipating. Imagine, we all depend on sun, but what is sun? Sun is actually a ball of gas where two different opposite forces are cancelling each other every second of our existence. This condition technically goes by the name condition of hydrostatic equilibrium, right? So sun is there, any star is there, and we can see it because of a thermonuclear fusion reaction at the core region. And though we look at the sun at the early morning or late evening, a beautiful disk, orangish disk, but sun is not so simple. If you see this picture taken during the total solar eclipse, huge amount of material on an average comes out from the surface of the sun every second, 1.6 million tons on an average. So when they move through the magnetic field of the sun, they produce this milky white radiation. And this picture taken by SDO, Solar Dynamical Observatory in 2012, that tells you sun is not a smooth object. Tremendous amount of explosions are happening on the surface of the sun. Huge amount of material gets thrown out, reaching a height of 10, 15, 20,000 kilometers, making beautiful arch and loops falls back onto the surface of the sun. Sometimes they get detached from the surface with such a force, they will flow past the whole solar system like a solar wind, sometimes solar storm. So sun is an amazing subject, is an amazing object because of the nuclear fusion reaction that is not only making it alive, but allowing it to radiate huge amount of energy, which when coming to Earth makes us live. We survive because of the sun's rays, sun's energy. So if you talk about the solar system, sun is the dominant character, but there are other characters as well. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and poor Pluto. Poor because in 2006, it has been officially demoted as a dwarf planet. But each of these objects is an enigma. Even our Earth, how much do we know about our Earth itself, about the interior? Forget about the other planets, but human mind, it tries to go forward. It tries to go venture out into the unknown. That's why maybe another 20 years, we'll be landing on Mars. Moon has already been conquered long time back, 60 years back almost, right, 50 years back. But other places, yes, maybe in the future, who knows? And there are these thousands and thousands and 100,000 pieces of rock, mostly residing between the orbit of Mars and Jupiter, going round the sun, called asteroids. Here in the picture, the red dots are the Apollo asteroids, whose orbit intersects the orbit of the Earth, thereby giving us a panic every time an asteroid coming towards the Earth, whether it is going to collide, right? And obviously, as I mentioned, comets. Beautiful objects with million-kilometer long tails, but the cometary head or nucleus is only 15 to 20 kilometers in diameter, made up of dirty ice, lot of ice, water ice, dry ice with lot of dirt inside. And as they come close to the sun in their elliptic orbit, because of the sun's heat, the ice melts, get ionized, vaporized, and you can see a million-kilometer long tail made mostly out of vapor. Enough of the solar system. Let us start our journey outside. Twinkle, twinkle, little star. The sky is amazingly beautiful. But you can ask a question, why can't we see this? Because the problem is with our eyes. There is something in our eyes called perception of vision. Within 1/10 of a second, whatever amount of light enters through our pupil and falls on the retina, the optic nerve immediately takes them to the back of our head to create an image. Our eyes cannot integrate light like a CCD chip. If our eyes were like a CCD chip of your mobile camera, looking in a particular direction for 10 hours, 20 hours, 30 hours, you could have seen Almost every dot in the sky is a star. And there are huge gas clouds. Are all the stars like sun? Answer is yes and no. Yes. Why? Because most of them, 91% of them, are burning hydrogen to helium at the core. Why no? Because they come in different initial masses, different surface temperature, and different chemical composition. If you take the mass, stars in general, on an average, come in the range of 0.08 to 150 times the mass of sun. But the mass of sun is 1.9 followed by 30 zeros, 1.9 into 10 to the power 30 kilograms. Because stars, solar system are not our focus today. Let us go into the concept of life and death of stars. But we know that stars, this huge amount of reservoir of energy, they are born from interstellar clouds of gas and dust. We cannot see most of them through our naked eyes. But in the sky, there are regions where you can see through your telescope, through your CCD cameras, integrating light for long hours. These clouds and also sometimes star formation processes. Nature, one of the best picture of nature, the Orion gas cloud, a star forming region. See the vibrancy of the color, the dimension that the beauty of nature provides us through these cosmic objects. See for yourself. Huge. How big? How big? If you can see these small globules over here, each globule inside has a fully formed stellar system, like our solar system. Think of the size. Universe is throwing a challenge to the human intellect. You think you are clever, right? Try to understand. Try to get the ultimate questions answered of nature. That brings me to the death. Death of a star basically means when all the nuclear fuel at the core gets converted from hydrogen to helium. But not in every case. The moment helium is reached, star is died. No, it doesn't happen that way. Stars whose initial mass, remember, initial mass at the time of their birth is within a range of 1 to 8 solar mass, like our sun, for example. How much hydrogen at the core? Sun will be burning, don't worry, sun will be burning for another 5 billion years, 500 crore years, right? But after 5 billion years, when all the hydrogen gets converted to helium, the thermonuclear fusion reaction will stop, energy production will stop, outward pressure will stop. As if something stops in the sun, but gravity is there, attractive. So sun will try to squeeze, become constrict, contract. As this is happening in the outer layer, just below the surface, there was still huge amount of hydrogen remaining. And because of the contraction, the temperature rises in this region as well, and ultimately reaches 1.5 crore degrees centigrade, which is enough again to burn 4 hydrogen to helium. The reaction that was happening at the core will start happening in the shell region. Again, energy is produced. Gas, when heated up, expands. Thus, the star becomes bigger and bigger. And after 500 crore years later, our sun will become bigger and bigger and bigger and ultimately touch the orbit of Earth. Bad thing. But don't worry, 500 crore years, you and I are not there. Whatever. At that phase, it will be called a red giant star. At the same time, the inside, the temperature rises there and rises to 10 million degrees centigrade. 100 million degrees centigrade, 10 crore degrees centigrade. And at that temperature, 3 helium nuclei as if come together, fuse together and produce a carbon nucleus. This helium to carbon transformation again produces energy and the star stops contracting. But soon, all the hydrogen gets transformed to helium and all the helium gets transformed to carbon. Then what happens? Since the initial mass of the star was in the lower range, there is not enough matter to produce a gravitational contraction to raise the temperature of the core to much higher level, where carbon will fuse, give rise to oxygen, sulfur, silicon, so on and so forth. So the inside becomes very hot, but small in the sky, called a white dwarf. Whereas by that time, the outside has become so big because the star was pulsating in this time to keep the hydrostatic equilibrium intact. And it creates a cloud-like structure in the outer periphery of the star, of the white dwarf, which is called the planetary nebula. Over millions of years, the planetary nebula dissipates, and the white dwarf, giving away all its heat, becomes very cold and either becomes a brown dwarf or a black dwarf. This may sound itself, forget about black holes, a science fiction story. No, my friend, in the sky, you can see the true images of this planetary nebula. And at the center, that bright dot is a white dwarf. Amazing. But what about stars? We are a little bigger. But before that, I should mention that in 1930s, it was a legend, Subramaniam Chandrasekhar, an Indian-born American physicist, who was working, trying to understand the theories of general relativity given by Einstein and how it is applied to cosmic objects, especially massive compact objects. And through his brilliant mind and brilliant work, he showed that if a white dwarf, mind you, and not any star, a compact white dwarf, if the mass of the white dwarf crosses a limit, then it doesn't remain a white dwarf. It becomes something which I'm just coming. But that limit is called the Chandrasekhar limit, 1.44 times the mass of Sun, for which he ultimately received the Nobel Prize. Almost 50 years later, though, but still he received it. That brings me to the subject of the explosive deaths of stars. Stars whose initial mass is roughly 8 to 25 times the mass of Sun. Because of their heaviness, because of their mass, at the center, hydrogen to helium, after that, helium to carbon, after that, oxygen, neon, magnesium, silicon, and ultimately it ends up at iron. Iron has the highest binding energy. You cannot force two iron nuclei to fuse and give rise to anything else. So the thermonuclear fusion reaction stops and the inside becomes an iron core, very hot. But these layers of hydrogen, helium, carbon, because of gravity, they are bound to fall inside. And the poor iron fellow has nowhere to go. As a result, when all these surfaces, all these layers, they are going towards the center, the iron fellow becomes incompressible almost, 10 to the power 17 kg per meter cube, nuclear density almost. And ultimately, there is an implosion, a kickback, and an implosion. And all these layers get lifted up, and the star explodes. At the point of explosion, the temperature can reach such a level, all the naturally occurring elements of the periodic table beyond iron, most of them can be made instantaneously. Not in big quantities, that's why they are called rare earth elements on Earth, right? So this supernova explosion is an expression of a violent, tremendously energetic, roughly 10 to the power 54 arcs per second. Sun is 10 to the power 33 arcs per second, the luminosity. It can outshine any star of any galaxy. So supernova are important. But again, in addition to telling us that all the materials that makes your body, iron, magnesium, zinc, potassium, sodium, maybe one day, millions, billions of years back, was formed only inside the core of a star. So our body is made up of stellar ash. We are fossils, like living fossils though, but we are all star children. This is a very oft-quoted statement. We are star children. But that is true scientifically as well. And what remains, that ball of iron, because of the compression, contraction, all matter loses their identity except neutrons. Protons, electrons combine, a lot of things happen, and the ball becomes full of neutrons, called a neutron star. And sometimes because of the tremendous spin, because it has to conserve its angular momentum. As it becomes smaller, the spinning rate becomes faster. Charged particles, they move across the magnetic axis of these neutron stars. And if the spinning axis is different from the magnetic axis, we see as if two such beams, such lights moving in space on one pole, creating as if a cone of light. And if our eyesight cuts that cone, we see a pulsar. But in the recent years, magnetars has also come into existence in our understanding. But there is a limit. Like white dwarf, more than 1.44 solar mass will explode as a supernova. But if the remnant of the supernova neutron star is within the range of 1.5 to 3 times the mass of sun, it's more or less fine. A little higher, it will not become visible at all. As if it will cease to exist physically. Yes, I'm talking about something called black holes, which is, I think, the most mysterious phenomena in our natural world. A lot of people have a lot of concept, mostly reading science fiction. Black holes, as if a hole. What is it? Can I jump into a hole, go to another dimension and backward in time, forward in time, all sorts of science fictions from our childhood we have read. And we have started imagining, believing black holes, oh, they are something we can talk about, but they are not physical. They are not real. And that is the whole issue of this 2020 Nobel Physics Prize. So initially, stars, because stars in its lifetime loses huge amount of their mass. So initially, if the star is roughly around 25 times or more than the sun, at the end of all this nuclear burning process, still they cannot hold itself in its integrity. And because of they're so heavy, that due to their own gravity, they shrink slowly after the nuclear fuel is completed, and ultimately end up in an extremely dense point, extremely dense, infinitely dense, and in general are called black holes. But this is one of the most simplistic definition of a black hole, because black hole is a test, is a challenge to our human understanding of nature, is a challenge to our mathematical ability to describe nature in a complete manner. And it is also a challenge to our intuitiveness in our thoughts, in trying to find out newer and newer mechanisms present in nature. So if you see on the upper panel, from a nebula, a gas cloud, average star, low mass star, massive stars, they are born. And ultimately, through different processes of becoming big, becoming luminous, becoming giants, becoming red giants, super giants, blue giants, planetary nebula, supernova, white dwarf, and neutron stars, the big ones end up into a black hole. So black hole ranges should be close to the mass of a star. But it is not so. Because in nature, they have found roughly 3 types of black hole. Till a couple of years back, only 2 types of black hole. Stellar black holes and supermassive black holes. Million to billion times the mass of sun. But in the recent times, scientists have started finding objects which indicate that there can be black holes of the range of, say, 1,000, 5,000 solar mass. So they are called IMBH, intermediate mass black holes. The whole concept started with, I think, long time back, right? 300, much more than 300 years back. Through this work of this genius, Newton, Isaac Newton, who gave us the laws of motion, who gave us a lot of other things. Actually, in addition with Leibniz, he also gave us calculus. At the same time, he gave us the concept for the very first time of a completely new idea that two bodies attract each other instantaneously by a force, the force of gravity. The story goes, the question of gravity came to his mind because he was walking down, and in an apple tree, an apple just fell on the ground. And he found that apple is falling, but it is falling faster and faster as it reaches the ground. So it is accelerating. And according to his laws of motion, accelerating bodies means there must be a force acting on it. Force equal to mass into acceleration. Second law, Newton's. So if it is accelerating, if the body is accelerating, where from the force is coming? What is that force? Who is forcing it to fall? And there came the beautiful concept of gravity, the universal gravitational law, where two bodies attract each other with equal amount of force given by the product of the masses of the two divided by the square of the distance between them and multiplied by an universal gravitational constant called capital G. These forces are equal, but suppose there is a big ball and a small ball. The small ball and the big ball are all facing the same force, but who will be starting to move depends on its mass. Because the force is same. If mass is small, acceleration should be much more. So the motion will be on the part of the small ball. And that's what happened in our solar system in everywhere. Sun is almost as if static, as if it is jiggling, because going round is barycenter of the sun and the other objects in the solar system, but it almost doing this, whereas other planets are going round the sun. So we all know that if we throw up a ball, it comes down. Who is to blame? The gravity, the Earth. But if we throw a rocket at a speed of 11 kilometers per second or more, it goes out of the Earth's orbit and goes beyond the Earth's effect of gravity. So the question of escape velocity, root over 2gm by r, comes into play. And we all know, depending upon the mass and the radius, for example, each planet has its own escape velocity. Somewhere you have to move very fast. For example, Jupiter, tremendous 70,000 more kilometers per second, whereas in Earth, it is only 11 kilometers per second. So escape velocity gives us the power, if we have it, to get out of the clutches of any gravitating object. But even after Newton, people started wondering what will happen if, because of gravity being attractive, a heavy object, a star maybe, collapses because of gravity, and since it cannot be stopped, it's almost a runaway process, and ultimately it will become so dense, it will not allow anything to come out of its surface, not even light, not even the photons. So we will not be able to see them. So these ideas were mooted first by a fantastic mathematician as well as a priest, English, John Michell. And just a couple of years later, by Pierre-Simon Laplace, who both spoke about presence of non-luminous bodies because of their mass. And they actually termed it as dark stars. Michel used graphical method to explain his concept, whereas Laplace, being Laplace, published a mathematical proof in 1799. So people, even scientists even that time, was wondering, if gravity is attractive, it will become smaller and smaller and attract everything. What happens when it is in a critical state? It is extremely small. This concept was already there. But then came the genius, the brilliance, the character of the 20th century, as told by the Time magazine, Albert Einstein. Albert Einstein is known for so many wonderful achievements, discoveries. He got his Nobel Prize for photoelectric effect. But according to me and to many people all across the world, and even in the future, they will realize the biggest contribution to our present understanding of nature, science, how it works, was his general theory of relativity. Because he was wondering of two things. Well, why space should be infinite? Who told you? He knew, he told, you know about space-time, right? Given during 1905 for a special theory of relativity. They're intricately linked up. 3 dimensions of space and 1 dimension of time. We know time is dynamic. It changes, continuously it changes, right? Every second it changes. Is space dynamic or static? Can acceleration can be mimicked by some motion? And he found yes. So he said, the instantaneous force of gravity as given by Newton probably is not the correct interpretation. At least near a huge concentration of mass. It is an object with its mass creating a curvature in the curved space-time. The degree of curvature depending upon how massive the object is. And this curvature will tell other bodies how to proceed that object following the curvature, even light. So this wonderful equation, G mu nu equal to kappa T mu nu. G mu nu giving you all the curvatures present everywhere in the universe. And T mu nu telling you all the mass and energy present at different locations of curvature. Beautiful equation connecting the two, right? So it's as if this is an imaginary thing. Don't think it happens like this in space-time, because you cannot go out of space-time. But just to visualize for my young friends for the webinar, as if in the space-time matrix, fabric, an object creates a curvature. So Einstein and his general theory of relativity gave us a fantastic quote, not by him, but by a later general theorist, that mass tells space how to get curved, and space tells mass how to move. That's why Earth is going around the sun doesn't mean that there is an invisible string, a gravitational attractive force, which is connecting them. It is the presence of the sun producing a curvature in the neighborhood, and Earth is just following that curvature, not falling into the sun because of its rotational motion, but going around in a closed orbit. So again, in terms of visualization, a massive object curves the space-time around us. Far from the object, space-time is nearly flat. That's the reason 10, 20, 100 light year away, another star is not rushing towards sun. It is far, far away, right? But close to the subject, as if the curvature forms a well where everybody dips in. They are lucky if they have a motion, they will not go and touch the bottom, but they will go round, going round these walls of the whale. So in Einstein picture of gravity, other objects, they can feel the curvature and are drawn into the well. Feel doesn't mean physically feel, but as if their motion understands, realizes that amount of curvature. Published in 1915, right? And distortion of space and time are most noticeable in the vicinity of large masses. So now you think of the escape velocity. In a normal star, light comes out, sun, emitted from the atmosphere of the sun, coming to us, almost as if straight away. But the more denser, the more compact the star becomes, like a neutron star. Here, even light rays trying to come out, move straight. Light travels in a straight line, class 5, 6. Because of the curvature of the space, they cannot move straight. So their paths, their trajectories, as it is called, will slowly get curved. And this situation can be very critical when at a point the central star has become so dense that light trying to come out cannot come out. It will fall back as if it remains within the region around that dense point. So you cannot see them, and it should be called a black hole because black means I cannot see it, no light getting emitted from it. So basically a black hole sharply carves the space-time around it. Again, far from the black hole, the space is flat. But as we go closer and closer, it is as if a well which is infinitely deep, or rather, the density of the object creating that curvature is infinite. Now, this is a problem for any physicist because even the mathematician, they don't very much love the words infinity or singularity. If it is almost a point dense thing, it is creating a singularity in space and time. Don't think there is a tear in the space and time as if something is falling and going through. It is not so simple, but as if there is a singularity and infinitely dense. So what does it mean? You cannot cope up with your standard mathematics. What is a singularity, or what is a point, and what is an infinity? A point has no dimension, volume 0. So what does it physically mean, right? But if a stellar core has a mass greater than about 2 to 3 solar mass, gravitational compression will overwhelm any and all forms of pressure, and stellar cores will collapse into what is known as a black hole. Fantastic story. 1915, within a couple of months, imagine a very, very reputed mathematician, Karl Scwarzschild, but he also was patriotic. So he was fighting for the Germans in the Russian front. And he became a lieutenant. He was so good at fighting. But at the leisure moments, he was trying to solve the Einstein equation. And then he realized he can solve it with a prescription of how to define distances in curved space, or rather, how to give the proper metric, which is given in the top, right? For most of us using a ruler, it is actually basically r square equal to x square plus y square plus z square. No coefficients, only x, y, and z to the power square. So r will be equal to square root of that. It is almost close to that, but much more bigger in its scope. And it doesn't bother about time being flat or curved. So this is most generalized notation of a metric given by Karl Scwarzschild. But to find an exact solution, he could not solve it directly, but has to assume something. And what he assumed? He assumed that on the assumption that the electric charge, mass, angular momentum, and something called cosmological constant and enigma are all 0. Basically, that means it is a static black hole. It is not moving, not rotating, not electrically charged, but it was a wonderful development. Einstein liked it very much. But when he said that when I do this calculation, I come to a point that at 2 regions, the whole concept of, forget about GR only, all the mathematical calculation as it breaks. One, at the very center of the object, the massive object, if it is contracting, and around the surface, around the object, where he found singularity. Almost undefined. What will happen? What will be the future of an object reaching that place? So basically, it was very puzzling, even to Einstein. And he said that, okay, as if this nice picture of a space-time getting curved and almost infinite, deep, well, and all that sort of stuff. And you were mentioning that there is a region beyond which an object passes, like a one-way membrane. It can never come out. Even lights from inside cannot come out of that surface. Event horizon, as it is called, as it was called. It's very disturbing. So mathematically it can happen, no doubt, but in real life, singularities, I am not very sure. So even the proponent, even the person who gave birth to generality or relativity, initially he was not very happy with singularities. But later on, as work went on with his GTR, they found that light is bent because light has to follow the shape, the size, shape of the space-time. So if space is curved, light will also get curved, it will bend. The event horizon then was discussed as a boundary inside which light is bent into a black hole. And approaching the event horizon, you can show, because of this extreme curvature, time slows down for an observer who is very, very far away. Basically, that means at that level, in a very simplistic level, you find a chair or a ball going inside a black hole. It can never happen that way, by the way. As you approach the event horizon, there will be something called a spaghettification. You will be stretched so much, ultimately nothing remains, only atoms and molecules, which also will get stretched out and ultimately fall into inside the event horizon. But you can never see actually an object falling into the black hole through an event horizon from a distant place because time has slowed down. And for observers, time stops at the horizon, right? So the formation of that black hole is complicated. Though I am just waving my hand saying it, big minds, brilliant minds, amazing mathematics, throughout the world, scientists are working on it. We are very lucky that our country presently also has a group of people, extremely talented scientists, theoretical physicists, who not only work in this field, but almost regularly do path-breaking works. But the path-breaking first was done by Einstein, obviously. So Karl Scwarzschild actually supported it with his fantastic calculation. Sadly, he died in 1916 also, Schwarzschild, of a disease which was contracted in the battlefield, whatever. So the formation of a black hole is complicated. It is a boundary shaped like a sphere for a static black hole. It either can rotate or may not rotate also. In very, very special circumstances, I'm not going to talk about that, it can slowly disappear as well, but I'm not talking about that today. And the boundary between a black hole and the rest of the universe is that event horizon, that one-way membrane. Don't think it's like a bubble surface. No, it's an imaginary surface. No matter exists at the surface. And matter, if one's crosses the black hole event horizon, can only be destined to reach the singularity at the center, which we are calling as black hole, as the name was given, as was told in the very beginning by a very famous scientist at Princeton, Archibald Wheeler. But there is a story also behind it. A story said, little prior to that, it was a reporter, a journalist. I do not know the veracity. I do not know whether it is correct. First, used the word black hole in describing these sort of concepts. And later on, in one of the lectures of Wheeler, one student got up and said, this can be called as black hole. It has already been mentioned. And Wheeler liked it very much. This is a story. I do not know that. Nobody, please don't take me to the court for saying this. But in general, now, popularly, we all know it was Wheeler, Archibald Wheeler, who coined the name of a black hole. And there is a region of space, as I mentioned, Schwarzschild has said. If something crosses, cannot come back. Even light cannot come out of that surface. It was given the name Schwarzschild radius. Right? Simple relation. 2 gm by c square. M in solar mass and R in, say, kilometers. If you do, you will find for a 3 solar mass star, if it becomes a black hole, its Schwarzschild radius will be only 9 kilometers. For our sun, it will never become a black hole. But think, imagine, science fiction. If sun becomes a black hole, then the Schwarzschild radius will be only 3 kilometers. And it will never happen. Impossibility, abnormality, and never can you even think of, but if still in your mind, imagination, Earth becomes a black hole. You know what will be the Schwarzschild radius? Only 9 millimeter. Right. So it's a region of space where from you cannot see the light coming out, black. On the surface, material falling in, but before falling, getting completely ionized. Then came a huge amount of activity. Somebody said, okay, if a black hole starts rotating, then what will happen? So he described the mathematics behind it. Roy Kerr, who is still alive. Then another person said, if it is rotating and also electrically charged, what happens? Ezra Newman, he gave a metric, Kerr-Newman black holes. Then, if the black hole is not rotating but sitting tight, but is charged. Two scientists, Reisner and Nordstrom, gave the mathematical description of how to approach the problem of that black hole. So, static, rotating, static but charged, rotating but charged. Basically, 4 types of black holes. How will you see it? You cannot see a black hole. But if there is a nearby star or an object, because of the intense gravity, material will come out and get drawn towards the black hole. But before falling onto the event horizon, they should be losing their angular momentum. As a result, they have to go very fast around that central object. And as they're going very fast, because of the tremendous friction and other thermal processes, copious amount of radiation will come out. And if you see the radiation in X-rays, for example, and without seeing anything, where from the radiation is coming? From the disk or from the center of the disk being called the accretion disk, because matter is accreting. You know that it's a signature of a black hole. Artist, not impression, digital impression, right? A black hole accretion disk. See the black region, that's the event horizon, it's a cut across, right? Cross section. And 2 jets of powerful particles, energized particles, coming out like searchlights, accretion disk and the jet in general. This is a very generic representation of a black hole. So you expect to see this. Have you seen this? Let us see. That brings me to the 2020 Nobel Physics Prize. Sir Roger Penrose, half of the Nobel Prize for what? Because of a paper, and the process of the work is started by the publication of the paper in 1965, which said black hole formation is a robust prediction of the general theory of relativity. That means whatever mathematical jugglery you do, whatever assumptions you make, can you do away with the singularity? He said, if you have to believe general theory of relativity, which can be applied for curved space-time in our universe, black hole formation is a certainty. Not only that, he just never said it by waving the hands. Tremendously complicated mathematical description of the properties of the event horizon and just its exterior neighborhood. And he did it also by a fantastic process, by a graphical representation, without much going into the deep mathematical concept of GTR, through graphical representation and basic concepts of gravity and how an object will move in presence of another object. He ultimately could keep it. But you must be reading in lost a lot of Indian newspaper, the Calcutta connection, the Indian connection. Yes, it is not just a gimmick by the journalist. There is a deep connection with the work of a legendary person. Sadly, I have used the word legend. He is not considered till today probably as a legend from the Indian context. I know hardly, I think the general people has heard about his name, and knows about him, or knows his work? Amol Kumar Raychaudhuri, born 1923. Right? What did he do? His life was very ups and downs in terms of the career. He wanted to do something, but he was forced almost to do something else. But still, he had the courage, the fortitude to come out with brilliant idea, right? So after the work of Karl Scwarzschild and others and all that, it was Amol Kumar Raychaudhuri who showed, without giving any assumption to his notion, like a spherical symmetry, as Karl Schwarzschild has said, that singularity is possible in space-time. Curved space-time, in a curved space-time, free particles and photons, that is how to describe their trajectory using a mathematical formulation and show how will they move. And he showed, in presence of a massive object, trajectories will converge and end up in a singularity. Beautiful. He employed the concept of geometry in that, differential geometries and others, but he told us that singularity cannot be done away with a mathematical jugglery. Like to a coordinate transformation, you can show the event horizon, Schwarzschild's event horizon is not actually a singularity. But here he showed it, that it will be a singularity. Amazing. But his concept was realistic, much more realistic. Black hole is static. No. There can be vorticity, rotation. There can be shear. If suppose in a flow of fluid, as the different layers are moving at different velocities, there can be a shear. So he added those components of rotation, vorticity, and shear. And in a much more generalized way, showed the results hint at the possibility of a singularity being present. And then the trajectories will converge. 1955. At the same time, he also thought about Big Bang. Why? Because we know space is expanding. 1930, Edwin Hubble has shown space is expanding. Earlier to that, theoreticians, Lemaitre, others, they have Friedman's model, they have all shown that, yes, we can handle an expanding universe. And Hubble showed it. So if it is expanding, if you go sufficiently back in time, can there be a situation where you have to say everything came from a dense singularity? So it is not that a star and death is singularity happening, but the birth of the universe itself. Can there be a singularity? Right? So these ideas also bothered him. He started working, but he's not very well known for that type of work, apart from the equation that he gave, that when he tried to find out whether space-time singularity appear in the theories because of special symmetries, one assumes, or do they appear because they are fairly common and generic feature of general relativity. So without the spherically symmetric condition, existence of singularity, mathematically shown by him, was the biggest contribution, right? So, but just a little bit, since it is an Indian connection, Kolkata connection, he had to find a very general approach, one which did not depend on the simplifying symmetries of the Einstein equation. And it has to be quintessentially geometrical. So he began with a study of neighboring paths of free particles and light rays in a very general curved spacetime, without assuming that such a spacetime emerged from the Einstein equation. And when he asked the question, do these paths converge together? And the answer was, yes, probably. Not probably, yes. So the answer emerged through a wonderful equation, which is now the famous, almost every academic scientific mind is talking in India about Raychaudhuri equation. Yes, that equation was called the Raychaudhuri equation, which provides the most general geometrical criteria for convergence or divergence of geodesics, that is paths, in a general curved spacetime. Amazing, right? So you can see the equation, and the omega being the vorticity, the sigma being the shear. And that was the foundation of the work started by Roger Penrose. By the way, this research work by AKR, he was a fantastic teacher. For 40, 50 years, he was teaching at the Presidency College, now an university. And all his students used to call him as AKR, Amol Kumar Raichand. I had the good opportunity of meeting him quite a number of times, talking to him, even interacting with him. That's a different story. He's an extremely gentle and polite person. But what a mind. Amazing. You know, now people who are doing PhDs, they have to have a supervisor who will guide them, supervise them. Without any supervisor, he wrote up that Raichaudhuri equation and straight away submitted to the university for a DSc, not even a PhD, DSc. And he was awarded the DSc. Do you know who was the examiner who highly praised his work? Archibald Wheeler. Yes, the person who is known to have coined the term black hole. So it's a wonderful thing that what a fantastic mind he had. And the sad thing, we hardly understand or know about his work, about the person. We know about each and every cinema, movie, heroes, stars, what they eat, what they do, where are they going, what dress they're wearing. But we do not know of this person. Post-independence India, his work can be considered as one of the greatest theoretical work, which has ignited the minds of people like Roger Penrose, Stephen Hawking, and made them work through and ultimately arrive at deductions about this enigmatic, esoteric, exotic black hole thing, and ultimately gave them the Nobel Prize. So Raichaudhuri's equation forms the basis of Penrose's mathematical proof of showing singularity is a logical and mathematical outcome of the general theory of relativity. And then a vigorous amount of activity, because this was given by Roger Penrose in 1965. And he was onto that because it is not only exciting, not only it was his field, not only it appealed to his brilliant mathematical mind, but in 1963, the first quasi-stellar radio sources, 3C48, was optically identified. Quasars were actually identified much earlier, 1950s or so, but it was 1963, 3C48, third Cambridge catalog, 48th object, radio, which was optically identified, and people realized from a very small amount of volume, huge amount of energy coming out, 10,000, 1 lakh times the energy of a whole galaxy coming out from a small region of space. Quasi-stellar radio sources. Why stellar? People thought they're like stars, but when they actually calculated their redshift, they found it billions and millions of light years away. Distant objects, still very bright, meaning extremely energetic, but small. So people started talking about the black hole. Oh, this is a black hole, but not a star, maybe. A supermassive black hole, huge black hole. And Penrose started his process of theoretical understanding around that time. So without spherical symmetry, singularity or a black hole can exist. He gave a mathematical description of the event horizon and its exterior. And he gave a fantastic graphical representation, which is known as Penrose diagram. At the same time, a very young student, energetic, brilliant mind, Stephen Hawking. They were trying to describe singularities, both forward and backward, meaning both about the black hole and the singularity at the beginning of time, Big Bang. One stellar, one universal, cosmic. Right. So Stephen Hawking was thinking about the cosmological aspects and talking about singularities. So both of them worked together with other collaborators and ultimately gave a robust mathematical concept in 1970. the singularity theorem, which forms the basis of this year's Nobel Prize in Physics, 50% of it, right? Later on, it was found not only quasars. Scientists analyzed that probably every galaxy center has a supermassive black hole. Some very visible because there is a lot of material near them. Some not that energetic, not an active galactic nuclei as it is called, like our Milky Way galaxy, right? So there was a tremendous exciting moment. And this is the singularity theorem. And you see in the references, Raychaudhuri, 1955, Physical Review, volume 98, 1123. And both of them has acknowledged Raychaudhuri, both Penrose, Stephen Hawking. And Penrose was, I think he loves India. Regularly, almost 3, 4, 5 years, he used to come to India. He came to Kolkata and met Professor Raychaudhuri. And Hawkins, I know, has spoken about Raychaudhuri to some people, some Indian students as well. And how is he? What is he doing now? But we don't know. We don't talk, we don't take him as a hero, as a role model. Somehow. So this is not my drawing, by the way. It is a very good article published in Resonance in 2008. Article written by Shayan Kaur, Professor Shayan Kaur, who is also one of the authorities of GTR and all that in our country. And you see, it is on the shoulder of a giant, Penrose and Hawking, as if plucked the apple, that mythical apple of Newton, who gave the concept of gravity for the very first time. But this time the apple is from the tree of general relativity, giving rise to concepts of a black hole, of a singularity. Now comes the other half, observational evidence. The Milky Way galaxy, galactic center. If you take the upper panel, this is the optical light, and you see as if a black stretch. Black stretch doesn't mean there is nothing. Huge amount of dust. Since dust absorbs optical light, from our point, 26,000 light years away from the central part of the galaxy, in a small region called the Orion arm of the broad spiral galaxy, that is Milky Way, we can't see anything there through proper white light. But if you go into the IR, infrared, the infrared light can pass through all that dust, pass through the depth, and ultimately can reach a telescope. And when they look deeper with infrared, X-rays, radio, they found something very funny. They found huge amount of gas as if coming out, getting thrown out like streamers. They found in X-ray tremendously luminous region, tremendously luminous. A very small region, maybe a star, but as if it is a central body in a lot of activities. Huge number of stars are going around that object very fast. That itself, the region is very bright, not that object, but the region is very bright. Since it is in the constellation of Sagittarius, it was given the name Sagittarius A star. So, in this fantastic video from European Southern Observatory, European Space Agency, ESA and ESO, you see, as you go deeper and deeper into the central region of our Milky Way galaxy, 100,000 light years across, around 20,000 crore stars. We are 26,000 light years away from this region. You see a very, very energetic, illuminated region. But with your technological marvels, as you go deeper and deeper, going to the cutting edge limit of technology that we can arrive at, you find at the very core, there are these lighted blobs, stars. And these stars are moving extremely fast. As if moving around a point, focusing around a point. And we have to understand that. So systematic observation and analysis of the galactic center over the last 30 years of stellar motion of closely spaced stars around almost a point earlier known as Sagittarius A star ultimately gave us the reality that there is a 4 million solar mass black hole at the center of the galaxy. At the beginning, it was 3.6, then the number changed a little bit, 4.2. Now, according to the Nobel Committee citation, it is exactly 4 million solar mass black hole. And you see the trajectories of the stars around a point called Sagittarius A, right? Around this Sagittarius A. Some has already made a complete circle in 20 years, 18 years. Some coming very close and passing by, zwick, very fast. So, huge number of scientists are involved in, believe me, in observing the central galactic black hole. But their leaders, the people who formulated, who planned, who actually observed, and then who analyzed, they and their groups of researchers, students, postdoctoral fellows, fellow scientists. One of them, the leader, was Andrea Ghez, Professor Andrea Ghez of University of California, Los Angeles. She used one of the most powerful telescopes on Earth, Keck 1 and Keck 2 telescope on Mauna Kea. 10-meter diameter, each of them, the mirror. How big are they? How powerful are they? Just to give you an idea, in India, take any major cities. Suppose all of the people are looking into the sky. All the lights entering all the eyes of all the people in a major city in 1 second is equivalent to the light gathered by Keck telescope in 1 second. Think of the power. And using these two telescopes, believe me, painstakingly for almost 20 years, they observed and then they analyzed, trying to see these closed orbits, very tightly bound orbits of closely spaced stars. But life is not easy because atmosphere is moving, dynamic. Air cells, they move continuously with different velocities, different sizes, creating the twinkling of stars, which can be characterized by a term called seeing, right? Because the atmosphere is continuously disturbed, a light passing through gets continuously refracted and bends, and ultimately you do not get to see a star image as a dot, almost like a dot, but a hazy blur. How to get about? One way is to do a speckle photograph. What is that? Take the snapshot of that object for a very brief fraction of a second time, but go on taking it 100, 1,000 times, then add up all of them digitally. But that also has a limit. So around 2000, a beautiful mechanism and a device that if I can find out how the atmosphere above the telescope is changing continuously, can I recreate digitally a correction to be done to the image, obtained image, so that the image becomes the real-like image, even if I've taken it above the atmosphere. And that was done by creating an artificial star, by shooting a powerful laser source, you can see in this picture down, right, onto the sky. It is not reaching the object, not the black hole, but around 100 kilometers above the surface. And as the light is getting reflected back, it is passing through all these atmospheric disturbances. So the image of this artificial star that I'm getting, I know what is the actual image of the star, of the laser star. Immediately it passes through a computer, instantaneously it does the correction and changes the mirror in such a way, not a very smooth surface in that sense, undulations, but minuscule undulation, so that we get a very clear image. Adaptive optics. Very complicated, right? And through adaptive optics system, they actually measured. You can see from 1995 onwards, they have done this measurement. And you see one star going round an orbit, another star called SO16, passing so close by Sagittarius A, A star, that it tells the region of the Sagittarius A singularity is not a big one. The region is small because if it is passing so close, otherwise it would have collided, but it has come out. That means this wonderful picture, the video tells us there is a supermassive compact object at the center of our galaxy. Reinhard Genzel, another person, amazing personality. Believe me, I have met him only once, very fleeting moments, when he represented Germany in Olympics, Olympics trial, not on the Olympics, sorry, right? Very good athlete. Even today, he regularly does this thing, but he's the director of the Max Planck Institute for Extraterrestrial Physics. In addition to University of California, Berkeley, emeritus professor, and Maximilian University of Bonn, he's also a professor. And using the VLT, Very Large Telescope in La Paranal in Chile, initially they used a single telescope of 8-meter diameter, 8.2 meter, did a lot of speckle interferometry, but couldn't get a good idea. So they went on and ultimately used all the 4 telescopes in tandem, and using the method of optical interferometry, got that beautiful image of the galactic center, right? Because this is actually an example of speckle imaging, as I told you. See how a object, the image continuously changes, right? It gets defocused, focused, defocused because of the disturbance, right? So using this 4, I think this is these are the wonders of the modern world. You talk about 7 wonders, 8 wonders. To me, these are the actual wonders of the world, and could get the image as well as the motion of the closest object, and also deduced that if this happens, a star comes and goes by, or a star orbits Sagittarius A star at a speed which was recorded at 7,650 kilometers per second, or around 2.5% the speed of light. Think about it, light. So they came to the concept this can happen if there is a central black hole of 4 million solar mass. End of the story of Nobel Prize Physics 2020. But future is there. It is exciting because they have found globs of light, stars, interacting with the galactic center black holes. What is the reason? What is the outcome? Called G stars. This was found by the UCLA group, University of California, under Gazes group. Then they have found tidal disruptive events. Star may be coming close, but then all breaking up into as if gaseous bodies, blobs, and then getting gobbled up, right? To find out exact motion of an object near a black hole, and how does gas behave with a black hole atmosphere. And obviously, much more finer tests and verification of GR is needed. So stellar black holes, intermediate black holes, supermassive black holes, I'm even forgetting about primordial microscopic black holes. That's a different story. Exciting, zoo. And in the meantime, we know, only last year, a year has passed when this result was declared. Messier 87, a supermassive giant galaxy, elliptical galaxy. But when you take the image in different wavelength bands, they have found powerful jets and extra luminosity at the center, right? 53 million light years away, they found 6.5 billion supermassive black hole at the center. Calculations, but simulations from a movie, that how it will look, not the black hole, the outside of the event horizon, the accretion disk. And lo and behold, in June 2019, they gave us the shadow of darkness, the picture of the shadow of darkness. One side is a little bright in the torus because of what is known as gravitational lensing effect, but it's an image of a supermassive black hole, directly imaged. So our galaxy, Milky Way, yes, they are going through an effort, but till now they are not yet fully successful, but simulations have been done. This is a simulation result, that if someday our central black hole is people can observe it, then they will probably get a picture like this, right? And talk about much deeper about all the theoretical understanding and expectation and predictions about a black hole. So it's imaging a black hole, testing of general relativity, understanding accretion around a black hole, and understanding how the jet genesis and collimation occurs, all on the shoulders of Roger Penrose's fantastic concepts, theoretical, and on the beautiful work by Andrea Ghez and Reinhard Genzel. And postscript, don't forget, probably also had a connection with a person who was from Kolkata, from India, Professor Amal Kumar Raichur. Thank you very much.
Thank you so much, sir. Really, it was an exciting presentation for all of us. It is very powerful, emotional, magical, and also supported by a wonderful and well-made, justified presentation. Really, we thank you so much for your knowledge and also the sharing of your knowledge, sir. Thank you. I hope, like me, all the participants would have enjoyed. At the same time, they might have learned a lot about this Nobel Prize as well as the subject. And I don't know if you wish to take one or two questions. Shall we pose some questions, or shall we wind up?
I am not a master in this field, but still I can. I'm a small student and a science communicator.
Already you have taken 1.5 hours. Actually, you have spoken. So
I'm sorry, I actually overshot because I was feeling very emotional, actually, in some sense.
Really, sir. Thank you so much. Actually, I hope if some of you require some question, you can very well unmute and start questioning. But one at a time, please. I hope people are not coming forward with question. That means they have understood everything.
And frankly speaking, not many, at least, people. I think only 30 participants in the at least in the Zoom meeting.
Right now only 30 participants are available. Yeah. Oh, that might be the reason. Okay, sir. Now let us wind up. And I request my colleague curator here, actually, Shri Balaji, MMK Balaji, to join and offer formal vote of thanks to the participants, Dr. Dwari and others participated in this event, sir. Thank you. Unmute. Sound.
Namaste, guys. It was a wonderful presentation, and it was the journey was started like the first year, and then you have taken a year, and then you went to.
Sound is very bad. Can you come here? Come quickly here. Quick.
I think we cannot hear this thing.
Yeah. Good evening, Dwari sir.
Yeah.
I think I am audible.
Yes, now.
Yeah. Sir, I'm Balaji. I'm working as curator at Regional Science Center. And hope you remember me. I think once we had a contact
Yes.
during our IAO last in 2018. I contacted you for taking some sessions at Nehru Science Center, Mumbai.
Right.
So that time, due to some problems, I think you have not come, and we have so we missed you that time, and we are fortunate to have you this time at this webinar, and really it was a wonderful presentation, and you have taken the entire journey.
Mr. Balaji, your voice is not clear. I think it's the connectivity issue, maybe.
Yeah, by the way, I will request the Freebird team, if they can sort of, they have recorded, or they can give me a link to the video of this presentation. Maybe send it through the Google Drive link and I can then access it.
Yes, sure, sir.
Yes,
I mean, we have
surely
recorded.
that will do.
Yes.
Sir, I am audible now. Is my voice
Yes,
clear?
yes, sir. Yeah, now it is clear. I think you can wrap it up first. Yeah.
Okay. So thanks for the wonderful lecture, sir. And on behalf of Regional Science Center, we thank you for giving your valuable time and giving this wonderful lecture. And also we thank our director, Sri Madan Gopal, for presenting in this lecture and giving the welcome address and addressing all the people. And also we thank all the participants who have participated in this webinar and gained the knowledge. And also especially we thank the team Deep and Amber from Freebirds Experiences for supporting us technically, and thank you one and all who have participated in this webinar. Thank you.
Yeah. So I think I will leave now.
Sure, sir. It was a pleasure having you here. Thank you for your time.